Alright, so let's discuss race from USACO 2020 January Contest Bronze Division. So okay, race is a greedy problem, and it's telling us just to go find the best algorithm possible. And, okay, so right here we have Bessie. Bessie is trying to run a race that's K long. She starts at a speed of 0. In a given second, she can either increase her speed by 1 meter per second, keep it unchanged, or decrease it by 1 meter. So she can accelerate, keep it constant, or decelerate by 1. And she can never be slower than 0. Bessie will always run towards the finish line, and she wants to finish after an integer amount of seconds. And she doesn't want to be running too quickly at the end, so she only wants to be traveling no more than X meters per second. So what's happening here is Bessie, she's in a race, right? And she wants to cross the finish line at X meters per second. So, okay. And she wants to see how fast she can do this. Now, rather than thinking about what constitutes and how can we like decrease the time, let's think about this for a second. So let's say we're gonna bring some math, okay? Sorry about this. So let's say you're moving at a constant speed of 1 meter per second. So let's say x was 1 meter per second. My question is it better just to run constantly at 1 meter per second? Or is it better to accelerate at, let's draw a curve. Okay, wait. Let's just draw a curve, okay? Or is it better just to always accelerate? Okay, that's a really bad representation, but here we are. Okay, so oh wait, that doesn't act. Sorry about this. Okay, more like this. Okay, so let's look at the positions. Okay, when does so in this suggests that Bessie is always accelerating, given a parabola. This shows that Bessie is at a constant speed. So what is better, for Bessie to always speed up, or for Bessie just to always stay at a constant speed? Well, obviously it's better for Bessie just to be at a to always be accelerating, because as you see here, Bessie arrives at this point way sooner than she does with this point when she's accelerating. So this means that we want Bessie to go as fast as she can and always accelerate until she can't and has to slow down. Basically, we want her to achieve the greatest speed possible before she has to start slowing down. If you think about it, it means that she can only go at, let's say x is 5. How fast can she go at her maximum? So let's say it's 6. So, okay, let's just draw this, because it'll probably be easier just to like represent this. So let's just draw a little graph here. Not exactly straight, but you should get the point. So this is time. Let's increase the size of the brush. So let's say this is time 0, okay? Okay, let's make this a different color as well, sorry. So let's say this is time 0. At time 1, she should increase her speed, okay? Time 2, she should keep increasing her speed. Now note this, in order for Bessie just to reach 5, she has to travel this much of a distance. She has to travel 1 meter plus 2 meters plus 3 and so on until she gets to 5 if x is equal to 5. Meaning at minimum she has to travel 15 meters. Okay? And from there, let's say k is equal to 25. From there, okay, we can see that if she does increase her speed, okay, you can add 6, it will be 21. But that means she has to also slow down in order for her to reach that point. To reach to reach 25 meters at the speed of, let's say, at the speed of 5 meters per second. So basically, what we're trying to do is maximize her speed. Because regardless, you will have some line that looks like, okay, let's just draw this line. You will have a line that basically looks like this. Well, of course, it's not exactly linear, it's more discrete. But you will have a line that looks like this. You will have X. Let's say X is indicated by this line. So let's call this X. We have X right here. And here's the maximum speed. And from there, she slows down at the same constant rate. And this is what it should look like. Because we're trying to maximize the speed and slow down to the point of her getting to X. We want to end off at X meters per second squared. Okay? And we're also trying to maximize how fast she can go in the race. So, with that being considered, let's look at a solution. So, we have set up a scanner. Okay, ignore the new file reader. Current USACO uses system input and output, but because this is 2020, but when did they change it? Was it like 2021? Thing is, they're using file input and output, so we didn't use print writer and new file reader. So for most USACO problems, you would have to use this in order to test your cases. If you don't want to like really do that, what you can do is go here, click test data, get the test data, and plug it in just to test. But honestly, it's preferable if you just follow their format and use file input and output. So okay, so we scan in K and N, K being the maximum, well, the length of the race, and N being number of test cases. Next, for each test case, we're gonna get X, which is the speed at end. This is gonna get our current speed. Okay, the reason why we start T at -1, well, it's because first of all, well, actually I could have just put -1 here, but the issue with my code was it was always 1 off for some reason. I think it's because here T plus right here. At time 1, the speed should be 1, but I started off at 0. Well, actually no, time 0, right? I think it was time, yeah. At time 0, she can increase her speed by 1. And it would be 1. So, because I started the speed at 0, I made T -1 just to indicate that. Of course, you can always just make this 0, but put -1 here. Still the same result. Okay, and then we have this. The distance speeding up and the distance slowing down. What we're talking about here is, oh yeah, by the way, this is going to be a velocity versus time graph. Sorry for the physics stuff, because, well, it has more calculus, but what we're trying to find is how far does versus time. Okay, what we're trying to find here is how much distance does Bessie travel when going at this speed. So at this point, how far does she travel? This point, how far does she travel? We use this. We use distance, this speeding up just to represent how far does she go while speeding up. And this slowing down just to indicate how far does she go while slow down. So this segment here, so let's just get a dotted line. Let's just make it red. Oh, not a dotted line. Let's just split it off. Split off the line right here. Wait, how? recording. Okay, 10 minutes. Sorry. So basically, this segment right here. This. Okay, so this segment right here is her time while distance while speeding up, and this segment right here is how far does Bessie go while slowing down. So first of all, now we're gonna have a while loop just to see if the distance speeding up plus the distance slowing down is less than k. Once it gets greater than k, we'll stop and print out t. Okay? Well, t minus 1 in this case, but yeah, I just print out an answer. Then we're going to check, is the speed greater or equal to x? And if it is, we're going to add the speed to slowing down, because when we're slowing down, we have to hit that speed. And we increase time by 1. Now, of course, the reason why we're using the equal sign here, okay, so when we're using the equal sign, because think about this, when we hit this point and we're starting to slow down, so we would have to use whether you take 1 second just to go from x plus 1 to x. It takes an entire second for Bessie just to do that. And if you're wondering, well, can this mess up like how the problem works? Well, think about it like this. What could happen is we're moving at let's say we're moving at this speed, we hit x, but then if x just so happens like we only need to go at x speed for the next second, it would consider like the last 2 seconds to be like constant at the speed of x. And also we still check right here. So the reason why we check right here just to see if it's greater than or equal to k, because it could be that when we slow down, we end up going faster or passing k, and therefore we need a break and print out the answer. Otherwise, we're gonna add the distance speeding up by speed, because the definition of distance is how far you go with a certain speed. Is like the like the addition of all your speeds. So you'll go at 1 meter per second. You travel 1, go 2. You'll end up traveling 3. This is hard to explain without calculus, but anyways, then we add 1 to speed, because Bessie can only increase her speed by 1 and increase time by 1. And of course, if this reaches x and it already works, so let's say for this case right here where she says, yeah, travels 1, 2, 3, 4, okay, this is like the case where this never executes. If these two instances never executes, that is, Bessie is just speeding up until she reaches x. And now you may be wondering, well, why does this work? Okay, why would it work for this case? So let's look at it. Okay, so at x equals 1, we're going to increase speed to 1, right? At time 1, speed should be 1. Well, that's time. Okay, yeah, so we travel 1 meter. Let's pull up Notepad. Okay. So let's just do it like how they establish. So our solution suggests that we increase time. This is our speed. This is our distance. Here our speed is 2, and our distance would be, I would say, 3. Here we would increase it to 3. 3, and our distance would be 6. Now what if we decrease the, now what if we keep it at 3? We have 2, 1, and this would be, wait, sorry, trying to figure out. would it be? I think it would, yeah, it would probably be somewhere along the lines of this. So yeah, so if we used our solution, it would have looked like that. Don't save. And I basically ran through the entire thing. I could have. If you still are confused or need like a re-explanation, I can easily redo this video and try to explain it better. But otherwise, the gist is you want to try to get the max. You are trying to get the maximum speed that best you can get. So that's why in our thing we're always increasing speed because we're always trying to speed up. And then whenever we need to slow down because it's greater than or equal to x, we just add the slowing down distance by that speed and increase time by 1 just to indicate that we'll be using a second just to slow down back to that original speed. So that way we account for the time slowing down while we speed up. So imagine like we're speeding up, we're just the moment we pass this k here past x, whenever we hit a point, we accommodate the same point across past this line. So like when we hit here, we accommodate for this part. When we hit here, we accommodate for this part, etc. Anyways, that's our solution, and see you next time.